Danny Chiao is an engineering lead at TechGen Feast Inc. and a Feast contributor. Previously, Danny was a technical lead at Google working on end-to-end machine learning problems within Google Workspace, helping build privacy-aware ML platforms, data pipelines, and working with research and product teams to deliver large-scale ML-powered enterprise functionality. Danny holds a bachelor's degree in computer science from MIT. And since this is his time, I'll hand off the mic. You take over.
Cool. So yes, we are here to talk about feature stores today. So let me just dive right in. Yeah, so I already kind of got the intro, but so I'll just kind of skip past this. So let me kind of like quickly first start with a quick plug for Feast. So what is Feast exactly? Feast is an open source feature store, and we have a pretty rich connector ecosystem already, and a lot of it is community powered. So we integrate with like GCP, AWS, Azure. Soon kind of Snowflake is coming on board as well, et cetera, et cetera. We have an active community with 2,000 plus members on Slack, and also bi-weekly community calls. And on the right here is kind of this hero image that we've thrown together, and I'll kind of be diving into some of these components in the talk. But below that, you can see here's a bunch of teams that some of them are running it, some of them are contributing it. Often it's both companies who try to use Feast, they understand the code base, and they can actually contribute back to make it work better for the use case, right? So quick agenda of the talk today. So I'll be talking about what are some common machine learning challenges that both data scientists and engineers face. What exactly is a feature store, and how does it help solve some of these challenges? There will be a brief demo that I'm going to showcase a Feast. And then I'm going to jump into some other stuff, which is like, how do you deploy Feast in a production environment? What are some typical patterns we see? And then I'm going to jump into some use cases and kind of show how Feast fits into somebody's specific problem space. And then I think that this is actually a little bit out of date. I'm not going to jump into the roadmap, but happy to take questions about that if people are interested. So yeah, I wanted to take a quick step back and highlight what does the machine learning pipeline look like from not even that long ago, like maybe in the last, just like a couple of years ago, this is the absolute norm. Even today, it's still fairly normal for this. What it looks like is if you're a data scientist or data engineer trying to build a model, you'll have some sort of historical data stored in a data lake, right? And maybe some part of this data lake is you have events that come in that will eventually pipe into the data lake. But ultimately, the data scientists are working mainly with this data lake, so like S3 files, databases, et cetera, right? And you'll run some sort of ETL pipeline where you make some sort of job, maybe it's like Spark, maybe it's a MapReduce job that will transform, join, and clean, prepare this data to generate features for the model training, right? So that's kind of what the data scientist does. And then at that point is where the engineers kind of take over, right? Like, okay, let me deploy this model you've trained that you think is really good. And I have to, this engineer has to then find, okay, we have this set of features that we need. Let me find all the places to get those features and then transform them in the same way. And then that's going to then feed some sort of output model prediction to the end user, right? Yeah, and then kind of you'll notice that there's also this arrow from this events and stream processing into the online features. That's just calling out that often you do need features at serving time, and oftentimes this is coming from events that are coming in real time. So yeah, I'm just going to jump into some challenges here. So one of the challenges here is, as a data scientist, generating training data is really hard. So we're looking primarily at the left side of this diagram here. And what do we mean by that? So first of all, there's a lot of infrastructure needs here that is exposed to the data scientist. So if you need to deal with a high volume of data, you're going to have to deal with some sort of distributed compute, distributed batch processing pipeline, such as a MapReduce job or a Spark job, right? Sometimes you want to do high volume transformations on this data, and that also requires kind of leveraging that compute. in many cases, you also need to have access to different kinds of event sources. And so you need some sort of stream processing layer that's built in here as well. Secondly, joins are really hard. And so what I'm referring to here is you often have a lot of different kinds of data you want to pull from to create. So for example, if you're trying to build the canonical like movie recommendation system, right? Like you have some features about a user who's trying to find movies to look at and some features around a movie. You got to join all these different data sources together. And it's often kind of tricky to build a point in time correct view of this. So you want to have the features accurate to that point in time. Like you don't want to have future values leaking in that can bias the model or give it an unfair advantage, and that'll lead to some training serving skew, right? And then finally, if you have a new feature idea, how do you actually go about doing that in this world? You would actually go back into this job and change some logic there, rerun this whole pipeline to load data from your data lake and generate the new training set, right? So in short, this can be fairly slow and complex. A lot of stuff has changed since then, including like the advent of data warehouses as a central layer of compute for this. And we're going to talk a little bit more about how Feast plays into that later on. The second bit here is that you're kind of working with two different environments. You have a training environment, which is the data scientist world, and you have a serving environment where the engineer comes into play, right? And there's a lot of nuances here. Some of them has to do with just like you have different requirements you need to satisfy, such as at serving time, you need low latency but high QPS. But at training time, you care about just processing a large amount of volume. But some other kind of things to call out here is, I mentioned training serving skew. There's also a lot of room for error here in your pipeline. Like often these pipelines to generate training data, you're doing some sort of data cleaning, some sort of downsampling, some sort of upsampling. And that can lead to a certain distribution of data that may be different from what you're seeing as serving time, right? And so that's kind of what we call training serving skew. It's like, well, my model said it was going to do really well in offline data, but it doesn't match what I see in online results, right? So that debugging flow is often caused because we have this disparity between these environments. The second key thing to clue into here is that where you pull data from could be different too, right? Like in at training time, you're pulling from this data lake. At serving time, pulling from data lake is too slow. So you need some other way to get features that are available. So every kind of team has their own different way of tackling this problem. And the final challenge I'm going to call out here is that there is a lot of duplication of efforts. So each kind of set of, whether you're like an ML engineer or data science team or whatever, when you're solving a new model, you generally kind of have to start from scratch. Like you maybe have some sort of shared knowledge with your peers, you can talk to people, but there's no real centralized means for collaboration on the coding level, right? And it's also very hard for you to have a layer of standardization, and everyone's kind of cleaning their data differently. Everyone's kind of transforming their data differently. And it's also just kind of hard to figure out, what is the prior here? Like, what if people already had success doing here? So that's another kind of duplication of effort challenge here. And so, yeah, enter the feature store. So what is a feature store? A feature store aims to specifically optimize for kind of these two personas we've defined here, like the data scientist and the engineer, where it helps manage ingestion and storage of the streaming and batch data so that data scientists no longer have to worry about like, how do I get all the data to kind of pipeline together? It also provides a standardized definition of features and transformations, and that is consistently applied for the data scientist and engineer. There no longer is a communication that you have to do. In the old world, a data scientist would have a model and they kind of just like throw that over the wall to the engineer and hope and pray that the engineer is able to accurately reproduce that, right? So feature stores will help ensure that consistency. And on top of that, there's also a discovery and registration component of this. So data scientists can define features and transformations and then learn what other data scientists are doing through kind of a discovery interface. I mentioned the point about point-in-time correctness, and feature stores typically will just manage a join for you. So you define kind of what's the rough shape and data sources that you care about, and then Feast or feature stores typically will help manage ensuring that point-in-time correctness. And finally, there is a component of validation, data quality monitoring, where you want to ensure that whatever data you're kind of that you're throwing into your training pipeline matches what your expectations are, that there's no outliers, and also that applies to at the serving time. So often feature stores will help manage with that layer of your system as well. Yeah, so this is just kind of reiterating that feature stores kind of break this up so that you don't need to have as much communication between these parties. On one side, whether you're like a data engineer or a data scientist, you can kind of just feed data in once, and now kind of everyone's okay with that, right? And then you have the model training, which is isolated by just you read from feast, and that's kind of all you need to worry about. And similarly, at the serving time, the engineers don't need to really talk to the data scientists. They can just look at what they've declared in feast and interface with that. Yeah, so now I'm going to go a little bit into kind of some of the details of how feast in particular works. So it's pretty standard flow. So a data scientist here will define features such as features that I've described in this kind of left area, and then register that with feature store feast. And then at that point, there will be some transformations that are executed depending on which path you take, right? Like if you're trying to get training data, then it's going to execute over that large batch of data that you care about. And in the online flow, you want that same execution transformation to be executed. So on the left side here, you can see on the top, we define a feature around kind of pointing to certain columns in a BigQuery table. And in the bottom there, you see a way to define transformations in feast, which we call on-demand feature views. And this lets you do row level transforms. So here you can see that there's some data that's available around lat long, and it will do some sort of geohashing for downstream usage, right? Yeah, this is kind of like getting back to kind of what I already talked about, but you want to have a consistent way to access this data, whether you're trying to serve features or get training data. And you can just see that in the interface, on the top box here, this is the API for calling, getting online features. And in the bottom, this is how you generate your training data. And they look fairly identical, right? And that's very much by design so that you can kind of just eyeball and recognize, yes, this is doing roughly the same thing. And finally, so this is an area that I think feature stores take a different stab at, depending on which feature store you are. But Feast currently has some sort of methods, some sort of interface by which you can write and publish features and then reuse them and discover them, right? So teams can easily reason about what they're doing. This is an area that we're looking to kind of expand more into and build a robust UI to kind of help you visualize everything that's happening. But right now, the raw data is available to users. So yeah, now I'm going to walk through and it's a somewhat contrived, but it's an end-to-end use case of how you might integrate this into an ML pipeline, right? So let me just set the scene here, right? You are trying to predict whether users are defaulting on their loan. You're getting kind of this, you want to build a model that will predict that for at serving time. And you have access to a bunch of historical data around loans and maybe some features around the user, and maybe some features even around like the location of where this loan is trying to happen, right? We have a GitHub repo that has all this code, so you can actually walk through it yourself very easily. I'm just going to kind of go through the salient points here, and you guys can run it yourself to see it happen in real time. So this here, I basically just wanted to kind of give you a quick sense of what the data we're working with here. So the bottom table here actually contains the target variable here, which is loan status. So you might think of this as like 1 is it kind of went through, and 0 there was a default or something like that, right? This middle is kind of some features around specifically the zip code as a primary key, and then this top one is really focused on this what looks like DOB SSN, and that's kind of date of birth, social security number, obviously fake data. We're not kind of showing social security numbers here, but that's kind of the user level features that we have access to. So yeah, in Feast, you would define an entity, and an entity really maps to you can think of this as a primary key. So in what I just described, you have some one table that was specifically focused on a person as the primary key, and then another one that was focused on like zip code specific information. So those will both be entities here. Here you can see that actually we're able to register in the data source as well. And there's other configuration that you can do to actually help set this up, but that's a one-time setup thing for just getting the right credentials and permissions and everything. Here, what you're seeing here is that there's actually a query that is querying over the S3 files that you have using Redshift, and that's being done through Spectrum to federate that query for all future kind of data transformations, et cetera. Yeah, next, kind of you define features. We've already kind of taken a look at this. This is mostly referencing that person entity that we defined before and calling out here some features and their types that we care about. And then you call feast apply. So this kind of looks like, for those of you who are familiar with tools like Terraform, it kind of looks like that. Like there will be a feast plan kind of method, a feast apply, and it uses kind of what you define as a declarative interface for registering features that you want and deploying the infrastructure to be able to be able to pull those features at training time or at serving time. And then there's this concept of materialization. So this is basically what this is doing is pulling the latest values that you need for online serving. So at serving time, you really just need the most recent data. You don't need a huge amount of history there just to be able to, you want just the data you need to be able to serve your prediction. And so that's what materialization is doing. It's loading data and then throwing that into what we call the online store, which is just a low latency store that we use to give you features at serving time. And yeah, and then you kind of fetch the features and you can do model training here. So you can see that we're calling that familiar get historical features interface here and getting the training data frame. And then we're able to kind of drop the target variable in this and just go ahead and train. So it's like super straightforward once you've already defined it. And at this point, you've basically transitioned to feature engineering out of your regular Python code and into the actual feature view kind of paradigm. But what that gives you is also now you're less bottlenecked by the engineer. Like often what we've heard is that you have a lot of data scientists and you have very few engineers to support all of them. And so this will really let you unblock the engineer, because the engineer can just say, let me just pull the same kind of set of features using Feast. And now I'm just ready to make my prediction. And it's all going to kind of be kind of up to date and transform consistently. Yeah, so kind of as a quick recap, we used Feast to register some data sources and define some features so that, and that's kind of done by some sort of like data engineer, right? Or an admin who has access to all the data sources. And then afterwards, the data scientist has a very clear interface where they know roughly what data sources exist. They can generate a point in time correct training set using the features they defined. And now they can train that model and prepare it for serving, and kind of it's super easy for the engineer to serve those predictions, and they no longer have to scour different data sources to fetch the right feature values they need. And yeah, so now I want to kind of dive into what are some common deployment patterns that we see with Feast. So how do you actually make this work? Like for this online serving stack, you often need to handle very high scale. So presumably there's some sort of like cloud, like a scalability component here, right? So this diagram on the right side roughly gets at one common pattern that we see, right? So on the bottom there, you see these batch sources, and this is like some sort of data warehouse or some sort of like, S3 or GCS where you store your data. And this is really, really optimized for compute because we're using the data warehouse as a compute layer. And people often use dbt as a way to do some pre-processing, some pre-transformations on this data, some data cleaning, and then they register that resultant data with Feast, right? There's also a way for you to register your events in the stream sources, such as with Kafka and Kinesis, and push that data directly to the online store. And I guess why do you really need that? The reason you want that is because you want access to very, very recent features. And the most recent version of that is coming from your stream events. So we allow you to kind of ingest that into Feast, and that will map well to kind of a certain batch source that you've defined. And then finally, kind of there is that materialization step I talked about. So we often see users will use something like Airflow to orchestrate and schedule materialization fairly regularly, depending on what their feature freshness requirements are, right? And then for training, you're kind of just done there. You can spin up the Feast SDK in your training environment, and now you can call it get historical features. For the serving component, you need to deploy this feature server somewhere to actually expose an interface to query these features. So there is a first-class integration that Feast has built with AWS Lambda. So you can kind of just very quickly, let me just advance. This is roughly how you would do it. So for the most part here, you just define feature server is enabled, and you kind of throw in your execution role. And now all you have to do is Feast apply, and that'll actually deploy the feature server for you and give you an endpoint that you can now just query from, right? So that's kind of what Feast has built. We also see people who will build packages up into a Docker image and deploy it into their own Kubernetes clusters. Yeah, and I guess the final point here is that people also do version their models with Feast. So there's a concept of a feature service, which is a collection of features that you often tie directly to a model. And you can actually, we have a guide on the Feast documentation, but you can save the exact set of features that you have with a specific model version, and now you can kind of track that with tools like MLflow, for example. Not going to dive kind of too deep into this diagram on the right, but we have users come to us and they have a variety of different needs, and they're able to integrate Feast fairly well. One big kind of current trend that we're seeing is that recommender systems are just really, really big. So that's kind of what this right side is. It's kind of painting, here's a picture of a recommender system that's trying to recommend users to items. And you can see that there's all these touch points signaled by this blue Feast icon. And Feast does kind of help you abstract some of the complexity out of what typically is actually still a fairly complex problem, which is building recommender systems. But we also see people coming to us for like fraud detection, which has very low latency requirements, or personalization. You need some sort of aggregate like historical preferences, for example, stored in an online store form, et cetera, et cetera. And yeah, that's all I had for you guys. So posted some links here. Any kind of questions? I left this diagram on the right hand just as like a quick reminder of what Feast does.
Starting to roll in from Keith. You mentioned Feast using MLflow. Have you used Feast with Kubeflow? What about Feast with both?
Yes. So with that question, we do actually have a pretty close partnership with Kubeflow, and we talk with them all the time. So there are folks who've used at least earlier versions of Feast with Kubeflow. I think there's some investigation on our part to help kind of close that gap again. But yeah, we definitely see people already using that today. The second question is around, is Feast useful in a 100% batch context? And actually, a lot of our users do come to us for this as well. And so there's two value adds that they get. One of them is that that point in time join is a complexity that they just don't want to manage, and results in a dramatic simplification of their overall stack. The other bit is, as teams scale up, they do want some sort of central way to discover features and collaborate on functionality. So people do, in both of those use cases, want to use feature stores. And then David, is Feast used and deployed widely? I guess that's kind of a hard question. It depends on what you mean by deployed widely. I had a kind of an earlier slide that calls out here's some users who are using it, but there's certainly a good mix of large companies or like medium to large size companies who are using Feast today. Some of them I can't really call out because they haven't publicly announced it for PR reasons. I can't really call them out, but there's a couple. There's a dozen listed on the website. And then we also have in our Slack channel, you can see all these people who are using it for personal projects or master's projects as well.
Right.
What is the relationship between Feast and Tecton? Sorry, go ahead.
Oh, any huge international banks using it?
I can't confirm or deny that. Mostly, yeah, I think anybody in that finance world
yeah, wink once for JP Morgan, wink twice for Goldman Sachs.
Yeah. Yeah, let me kind of get through some of the other questions. So like, what's the relationship between Feast and Tecton? So Tecton is one of the main contributors to Feast. That being said, so we have a couple of official maintainers. We have Gojek, who actually originally created Feast. And then there's also Twitter and Shopify are both active maintainers. So they're using it in their internal ML systems to build their internal feature stores on top of Feast. So kind of there's a couple of like key maintainers, but generally kind of Feast, you can think of Feast as they're trying to optimize for different goals here. Like Tecton's obviously a business, and Feast is more trying to solve for the community issues. And so there are definitely cases where we clash in terms of like, oh, what do we prioritize? And it ends up being different, right? So but Tecton is kind of a key contributor to Feast today.
Thank you so much for being a speaker this year.
Yeah, of course.
You enjoy the rest of the conference and have a wonderful day.
Sounds good. Thank you.